So now that we've talked about pKa's of the four halogen acids from the previous module, we're going to try to apply this concept to talking about equilibrium. So if we wanted to take a very generic acid-base equilibrium and draw it up on the board, we might show something like this. So this molecule right here is acetic acid. Vinegar that you have in your kitchen is very dilute, has very dilute quantities of acetic acid. So if we took this very concentrated acetic acid and we combined it with water, we could set up an acid-base equilibrium. Whenever you see these arrows, it's very important to remember that what we're saying is that the reaction can go forward, but there's also the potential for the reaction to reverse and go back and forth. Okay, so it's not a static one-way street. So if we were to draw the acid-base equilibrium for this, you could try to figure out which one of these is the acid and which one of these is the base, so we could draw the conjugate acid and the conjugate base. So it might not be obvious at the very beginning which of these two is the acid and which one is the base, but what we can do is we can actually utilize these pKa's to try to help us make this decision. So if you look at the in the literature, you'll find that pKa for the carboxylic acid in general is about 4.7, and the pKa for water is about 15. And of the two, the carboxylic acid has the smaller pKa, so the acetic acid is going to be acting as the acid, unsurprisingly, right? So now what we're going to see is that this carboxylic acid right here is going to get deprotonated, and we'll get a negatively charged oxygen, and on the other side we'll get this water which has now been protonated. Okay, so the way we can very generically talk about this relationship is that our carboxylic acid is acting as our acid, and then water is just water. And then if we look on the other end, we now have the conjugate base of this carboxylic acid. So we give this guy a name. His name is A-, and then H3O plus is again just H3O plus. And so the way we can talk about this equilibrium, you really need to envision this as a sliding scale going back and forth. In some molecules, their acid-base equilibrium lies really far to the right, and some lie really far to the left. So the way we describe this equilibrium, or just to what extent we actually go to the right, is we can set up this equilibrium constant or this acid acidity constant called Ka, and we can refer to this Ka as follows. So we can put the products in the numerator, so we can try to talk about the concentration of the products, and we'll put those over here. Okay, so and we ignore water because we assume that the concentration of water is constant for both sides of the equation, so they just cancel out. If we have a really high concentration of these guys on the right, then these guys are going to be very big, and Ka is going to be very big. So what we'll see is that large Ka's is going to represent something that's very acidic. If you have very small pKa's or very small Ka's, that's going to equal something, or that's going to represent an acid which is not very acidic. Okay, so again, if you think about it, if you have a very small pKa, what that must mean is that this number in the denominator is very big. We have a lot more Ha than A. Okay, and so then from there, we can talk about how pKa is related to Ka. So pKa right here, pKa is going to equal negative log of the Ka. And so what we'll find from that is that we have an inversion of this relationship, where you actually have small pKa's, again basically exactly what we found for the halogen examples in the previous module. Small pKa's are going to be very acidic, and then large pKa's are going to be not very acidic. Just to give an example, let's talk about Ka's and how they relate to pKa's with a molecule that we already know. So if we go back to HCl, if you've memorized the pKa for HCl, that would be you would know that the pKa for the HCl is -6. So let's try to relate the Ka, or the equilibrium constant for HCl, to its pKa. So if you look at HCl, we'll find that its Ka, if you look in the literature, is going to be very big. The pKa is going to be equal to the negative log base 10 of the Ka, which is 10 to the 6. So here what we can do is these just cancel out, some basic math, and we get a value of -6, which is, again, in the previous module we said that the pKa for the HCl is -6. So this works out perfectly. So what we've just done is, tried to relate Ka to pKa. So acetic acid, if you look in the literature, its Ka, or equilibrium constant, is 1.74 times 10 to the -5. Okay, so then its pKa is going to be equal to negative log base 10 of 1.74 times 10 to the -5. And then if you actually do the math on your calculator, you'll find the pKa is 4.7. Okay, a point to make here is that if you look at pKa's, it's very tempting to, try to think about these in units of, 1 base unit. So the difference between -6 and 4.7 doesn't look like it's a very big difference. So -7 to 4.7, that's about 11 units of difference. But that's not saying that acetic acid is 11 times less acidic than HCl. You have to remember that we're working on a logarithmic scale. So what we see here is that acetic acid is actually 1 with about 11 zeros behind it less acidic than HCl. So there is a huge difference in terms of acidity.